Yep, thanks, Patrick. So it is my pleasure to welcome today's speaker, Radek, and he will be talking about effective and multisymplectic forms of PDEs. So you can start, and you can also tell us why are you planning to do this in two parts, and what will be in the first part and what will be in the second part, just so everyone knows.
Sure. So hello, everybody. Thanks for the possibility to present these kind of things here. It's always nice to share some ideas and work. So the reason why I decided to split it into two parts, firstly, I noticed that there is quite a lot of empty slots in the seminar. And I was thinking, not that it is necessary to split this talk in two parts, because a lot of those things are not really very complicated, but there are numerous, there is quite a lot of notation, numerous namings and definitions which might not be completely, not everybody is maybe completely familiar with those things, although it's very often just some basic basic notions from differential forms, contact and symplectic calculus, and quite basic, yeah, but not all the notions I think are completely well known to everybody. So because the second part will be mainly computational and applying all the notions, I thought that it would be unnecessarily pity if I think the nice things that we can see from the computations, if it would be somehow covered by all the definitions and names. Yeah, so in this sort of a vague rationale for why I decided to put it into two parts. So in the first part, we will see the basic geometrical setup. We will recall some basic notions. I assume a lot of those things are known to everybody, but just to be on the safe side, we'll recall almost everything that we need. And then in the second part, we will use the constructions and the tools described in this first part to apply it on specific partial differential equations and see how it can be employed. The main idea of this talk is to use or to show how the contact and mainly symplectic geometry together with multisymplectic geometry can be applied in the context of some interesting partial differential equations, interesting mainly in the context of self-dual or anti-self-dual theories such as Plebanski equations or Grand equation, Hughes-Sine equation, and what we can do with the fact that those equations can be represented by some nice differential forms, and that the symplectic calculus can be applied there. Also, we will see, I will end with this today, that there is the notion of multisymplectic forms and certain differential forms that represent those type of equations we will be dealing with. So certain differential forms can be associated to or can give rise to so-called multisymplectic forms and then multisymplectic geometry. And we can again see some nice geometric features regarding that. So I suggest we begin. Okay, so today overview, contact symplectic and multisymplectic structures. The multisymplectic structures will be defined very briefly, just the definition of the notion of multisymplectic form at the very end. And maybe we'll be dealing with symplectic structures, but the generalization is very straightforward, as we will see. And then we will see what kind of tools we can develop using the contact and symplectic geometry. We'll be living mainly, as a matter of fact, we'll be in this talk, we'll be living only on J1M, the first jet space of smooth functions over M, where M is a smooth manifold. We will develop the notion of Euler operator, and we will see how this operator can be related to variational problems. And that's more or less it. So let's go to work. So as I said, the main aim is to use contact and symplectic structure. Mainly, we will be dealing, as I said, on J1M, and we want to investigate the relation between certain PDEs and whether there is whether we can find Lagrangian for them, or at least whether we can say, for example, that there is no Lagrangian for them. Then we can also use somehow the link between certain effective and multisymplectic forms. The notion of effective forms we will see later on is a crucial notion in this talk. And once we have the connection to multisymplectic forms, we can say something interesting about the geometrical features of the solution space. Yeah? Not that we would be capable of describing the solutions explicitly, but at least we can say something from the geometrical perspective. And sort of a long shot would be the point 3, which we will cover probably the next time, at least to some extent, because this is work that is in progress, and many things remained open so far. And it's the possible extension of the above case to the situation of more than one function. So we will be dealing with only one function of arbitrarily many variables. In the next talk, we'll be dealing particularly with the dimension 4. So our functions will be depending on 4 variables. But the setup which we'll be developing here will be for arbitrarily many finite number of variables. And all our considerations are local. We do not assume some global abstractions, yes, so just local things, although I will everywhere write M for smooth manifold, and it will look like we are dealing globally, but all considerations are local. So just to fix notation, if there is some question about the notation, I hope there is none. I try to keep it as simple as possible. So just check this out. M smooth manifold, Q mu local coordinates on M, Tm the tangent bundle, the corresponding local fiber coordinates of Tm given by local coordinates on M, T star the cotangent bundle, Q p local coordinates on T star, phi a smooth real function on M. Now we want to employ the equivalent of a smooth function as a section of the trivial line bundle M times R to M, yeah? So the section will be from M to M times R. And this then enables us to see the one-jets of function as sections of the prolongation of this projection. Yeah. Then standard notation, phi mu is just derivative in the direction of Q mu. J1 phi is the first jet of phi. And sorry. And J1m is the space of all one-jets of smooth functions over M. The local coordinates on J1 would be denoted Q mu, U, P, Ni. So Q mu stands for base coordinates. U stands for coordinates related to the function phi, to real scalar field. And P, Ni stands for derivatives of phi. So those are the coordinates on J1 that we'll be using. So let us recall some basic facts about the bundle of one jet. So J1m is not only a smooth manifold, but it's a smooth manifold which can be equipped with, or which has these type of coordinates Q, U, P, but is also a bundle over M. And as I mentioned, the bundle projection J1m to M is given by the first prolongation of this projection from M times R to M. Yeah, so this is the trivial line bundle. We have a projection on M. We can consider the first prolongation, and this will be the projection from the space of all one jets of smooth functions over M down to M. This is a very general thing. The similar idea holds also for higher jets, and there is some sort of hierarchy of projections, but we will not be dealing with higher jets at all. And this is the setup we'll be fixed on. So as I said, every function seen as a section of the trivial line bundle defines a corresponding section of the first jet bundle. And this is a coordinate expression of the section. So just notice how the pullback of coordinates functions works. So the pullback of Q mu is again Q mu. The pullback of U is phi, the function itself. And as I said, the pullback of P mu will be the corresponding mu derivative or derivative in the direction of Q mu of the field phi. Notice interesting identification. We can identify J1m with this direct product. Okay, so if everything is clear so far, again, just fixing notation and recalling some basic facts.
I have a stupid question. What is your abbreviation MA?
Sorry? Which abbreviation? Yeah. I haven't noted. Sorry, I haven't said it because I essentially want to exclude this naming because it is not very necessary for this talk. But we will be dealing with so-called Monge-Ampere operators, and essentially these operators are defined as via the pullback along these sections J1 phi. Yeah, so it might almost be confusing to call those operators Monge-Ampere operators, but in fact, it is a natural generalization because those operators give rise to generalization of Monge-Ampere equations. Yeah, the standard Monge-Ampere equations that probably many of you know. But we don't need this naming, and we will see later on why. But MA stands for Monge-Ampere. Okay. So sorry for that if it is confusing. I hope it is not confusing too much. So let me recall the notion of a contact structure on a manifold. So when we are speaking about contact structure on a smooth manifold, we mean a distribution over the manifold, so some subset of the tangent bundle. Distribution, I guess everybody knows. If not, then just ask. But I assume the knowledge of that, at least basic. And the distribution is such that its codimension is 1, meaning the dimension is 1 less than the dimension of the tangent bundle. And essentially, what I want to say by this, or what is expressed by this few lines, is that the distribution is completely non-integrable. Yeah, and this means that locally we can pick a omega 1 form, and the distribution will be given as a kernel of this form. If the 2 form is non-degenerate, then we call the D given by kernel of this form contact structure. Yeah, and this expresses the fact that D is completely non-integrable. Yeah. So if M is equipped with such a structure, we call it contact manifold. And the key observation is that the first jet space is in fact a contact manifold. And the contact distribution, which we are dealing with, will be in fact a Cartan distribution. So every jet bundle of arbitrary high order contains or has a natural notion of Cartan distributions, but only for J1M, this Cartan distribution is such that it is in fact a contact structure. It is a contact distribution. And we don't need this geometric definition of that it's spanned by tangent spaces of graphs of.
What's the difference between a Cartan distribution and a distribution?
Well, Cartan distribution is a specific distribution, right? In the same sense as contact distribution is a specific distribution.
Okay, so what's the definition of a Cartan distribution?
Cartan distribution is something which is spanned by tangent spaces of graphs, all possible sections of J1 phi. But maybe a better way of seeing what the Cartan distribution is by description of the form that describes the distribution. Yeah, because this will be, I think, much more familiar. Yeah. So it is spanned, in fact, by this du minus p mu dq mu 1 form. Yeah, this is the local description of the form that has the kernel, which is the Cartan distribution. Yeah. So if you pull back this form, you get always 0 for arbitrary phi. Okay. So that's the Cartan distribution. Does that somehow answer the question?
Yes. Yeah. So it's just the normal. I guess it has 2 names, Cartan something. Anyway, it's what you write there in the middle.
Yeah, because this,
yeah.
You know,
I was just confused on the previous page where it wasn't explained what it was.
Yeah, the previous definition, which I don't want to employ, but it's dually captured by the 1 form, is this. Yeah, that it's spanned by tangent spaces of graphs of all sections, where J1 phi I understand as a section of from M down up to the J1, right? So it's like a dual picture. I hope there is no mistake in that. Yeah. So, but notice that the Cartan distribution of J1M is described by something which is given canonically. We have a canonical identification of J1M and J1M with R times T star M, and we have projection on the first factor. And then we also have a tautological one form on T star M. And if we consider this guy, then that's in fact a contact form. Yeah. And this is local expression of this form. Okay. Of course, we assume always summation convention when we see repeated indices. Of course, we don't. I mean, like in this type of expression, we assume summation convention. So the contact distribution or Cartan distribution in the sense of J1M, yeah, this is the same thing, has the notion of, or defines the notion of Reap field, which somehow describes how the distribution is living in the tangent bundle, right? And the Reap field is given by the following conditions. Yeah, so the main condition is the first one, right? That it's in the kernel of the exterior derivative of C. The second condition is just some normalization condition, which enables us to work with the Reap field in a nice coordinate form, the most simple one. Yeah. So this is a one-dimensional. The one-dimensional subbundle spanned by this kernel of DC is described by this Reap field. Okay. So what we see here is that the whole tangent bundle of J1M splits into the kernel of C and kernel of DC. We have this kind of splitting. And this is also important observation, because this splitting, in fact, gives us the possibility to work in the symplectic setup, because the DC, the exterior derivative of the contact form, restricts to a symplectic form on C. And so if you notice the coordinate expression 5, this is a quite standard symplectic, I mean like standard symplectic form, right, locally. And it is non-degenerate only on C. So what we want to do is we want to always somehow project our object of interest, mainly some differential forms, to the subspace of forms which degenerate along the Reap field. And we will see in few slides ahead, we will see the projection operator that does that for us. Yeah, that projects arbitrary K form to a K form which degenerates along this guy Xi. Okay. So since we have the non-degeneracy of omega on C on the distribution, we can consider the dual vector x omega, which is simply locally has this nice expression. And we have so-called bottom operator, which simply means contraction with x omega. Yeah. Our convention is such that if we want to contract a two vector with the form, and notice this expression, del q wedge del p, then the contraction with alpha would be first contract with q and then with p. Yeah, so the position would swap. Okay. So there is also natural notion of top operator, which is simply wedging with the symplectic form, but we do not need this in this talk. Although it is quite interesting, because using the bottom and top operator, we can define. I mean, if you compute the commutation relation of bottom and top operator, where I recall top is just wedging with symplectic form, then in fact it satisfies the relation how they are called. Eilenberg-Chevalier relations, this like...
Yeah, it's assault to algebra. Right?
Yeah, exactly. And we will see later on the Hodge-Lepage decomposition, and this decomposition was proved precisely with the representation of, with the theory of representation of SL2. Okay, so now let us see Okay, I don't have a correct bullets up in the, now we should be in the space, I mean in the section of operators already, yeah? So don't be confused with the description in the heading. So this is in fact the Monge-Ampere operator that I didn't want it to call Monge-Ampere, because it's not always called Monge-Ampere in every literature. So what do we have? So consider n form on J1m. Yeah, notice that if m is n-dimensional, J1m is 2n plus 1 dimensional. So there is plenty of n forms on J1m. Yeah, but those n forms are quite special because we can pull them back along the sections J1 phi to obtain n forms on the base manifold. And this is just the one-dimensional subspace, right? So we can define, if we fix omega and we take phi, we can define this operator as a pullback of omega along phi. Yeah? This means that if we fix omega for every phi, assuming that we have fixed some, that we have fixed some volume for on M down on the base manifold, then this expression describes equation, partial differential equation, right? And it is called the Monge-Ampere equation. Now, the important observation is that once we have an equation and we want to represent this equation by differential form, differential n form, this description is not unique. Yeah, this representation is not unique. So the ambiguity is given by the fact that if we pull back down the contact form, it's always 0 for every phi. Along every phi, if we pull back down C, it will be always 0. This means that if we take an n form on J1n, which contains C in its decomposition somehow, or the exterior derivative of C, then the operator will yield 0. It will be an empty operator. Or, I mean, like the equation will be empty, right? And this leads to the notion of effective form. So two definitions of effective forms. So one will be this sort of algebraic, which, or maybe, how to say, cohomological, yeah? It is quite useful because it defines nicely what an effective form is. So we want to get rid of this ambiguity in the Monge-Ampere operators, or these operators given in the previous slide by 7, and the corresponding equations. And the ideal generated by C and its exterior derivative is precisely the ideal of all forms that generate empty equations. And so the redundancy in the Monge-Ampere equations defined in the previous slide can be expressed like this. Whenever we have n form in this ideal, then it will, for every phi, the corresponding equation will be 0. So we call effective form the form which, or a class, equivalence class, which is element of this space. Yeah, we simply factor out the redundancy. Yeah, but to compute with this definition is not so useful. I mean, it's not computationally useful definition. So there is another one, equivalent definition of effective forms, and it can be expressed like this. So first of all, we assume that k is smaller or equal n. This is the same as in the previous definition. But algebraically, we can define it as effective forms are those which are degenerate along the Reeb field, meaning that they are living on the Cartan distribution or contact distribution, and the bottom operator of them is 0. Yeah, I recall that bottom operator is contraction with the dual to the symplectic form. And in this case, omega is called effective. And the interesting fact about effective forms will be on the, I think, on the next slide, which says that to every form, I have a corresponding effective part, which is given uniquely. Yeah. So before we see the theorem, just consider example. Take dq1 of dqn, which is an n form on J1m, quite nice one. If we pull back down this form, we get a volume form on M. in the coordinate expression, and it is effective. Yeah, the condition 1 and condition 2 from 8, yeah, is easily satisfied. I haven't maybe written the coordinate expression of the RIP field. I'm not sure. Let me check. I don't know. No. So from the definition or the defining equations of the RIP field 3, it follows that the coordinate expression of the RIP field is simply del over del u. Yeah, it's just the partial derivative in the direction of u. And then it can be quite easily seen that this guy, if we contract it with del over del u, is 0, and similarly holds true for the bottom operator. Moreover, if we pick arbitrary smooth function on J1m and construct L beta, which in fact can be shown that L beta locally is the most general form, is most general n form, which gives rise to a first order Lagrangian down on the base if we pull it back on m, pull it down on m. Yeah, so L beta is in fact something which is the most general thing that give rise to first order Lagrangians in the standard sense on the base manifold. And this guy L beta is effective as well. Okay, so the key theorem that enables us to do some computations is the following: Hodge-Lepage, or also sometimes referred to Hodge-Lepage-Lishagin decomposition, proved by Valentin-Lishagin in 1979, is the following. Consider that we have an N form, K form, which degenerates along the RIP field, or in other words, is sort of living on the Cartan distribution. Then it can be uniquely decomposed, as 9 describes, and all the alpha i's are uniquely given effective forms. But most importantly, the alpha 0 has the same degree. If alpha is K form, then alpha 0 is also K form, and it's given uniquely. So every form, every K form has its unique effective part. So in other words, if I take a partial differential equation and I want to represent it by some differential form, then I know that although there is some ambiguity in this representation, I always have a one specific effective form, one specific guy in this class, which is uniquely given. It's possible to compute it. It's possible to compute it algorithmically, and it represents uniquely the equation. Yeah, so which is quite nice, and we will use it the next time in somehow dealing with the possibility of or dealing with existence of Lagrangian for a given partial differential equation. Yeah, so that's it. And as I promised earlier, if you want to be dealing with forms that are degenerate along the RIP field, and once again, why we want to do this? We want to do this because on the Cartan distribution, the exterior derivative of the contact form or Cartan form, the same thing in the context of J1m, the exterior derivative of this one form, i.e. this 2 form, is non-degenerate and thus symplectic. Yeah, so this projection is very important for us. And it's defined by 10. It's projection in the standard sense, so p squared equals p. And whenever I have a form which already is degenerate alongside, then the p leaves it as it is. And then we can define by 11 the projected derivative. And why do we do so? Because if we take a form which is degenerate along the RIP field, and if we compute the exterior derivative, the property of being degenerate along RIP field is not preserved by standard exterior derivative. So we need to consider this simple composition, this projected derivative. Okay. Okay, and now we are all set up to, we are all prepared to define the Euler operator. And it is defined like this. This dp composed with bottom operator composed with dp plus the lead derivative along the RIP field. So this is interesting operator. It's not completely obvious, at least it was not to me obvious why it is defined in this way. But as a matter of fact, this expression 12 follows from cohomological considerations. So we can, if we want to compute cohomologies, and include the notion of effective forms, so be dealing with only K forms which are factorized by this ideal that you have seen before, ideal generated by the contact form and its exterior derivative, then in fact in K equals n, am I saying it correctly? Well, I don't want to go into details because I didn't prepare this completely thoroughly, this cohomological stuff, but the form of Euler operator follows up as a condition on the existence of closed form in certain cohomological class in computation of effective cohomologies. Okay, so it's not just like pulled up from the thumb. It's something that really pops out from very natural considerations. And now the properties of this Euler operator, it satisfies many properties, but the most important for us is that it's a zero order operator. It preserves the degree of a form. It preserves effectivity of forms. So once I have an effective form, i.e. satisfying form which satisfies that it's degenerate along the Riemann field, and it vanish on the bottom operator, then these two properties are preserved. But notice that it doesn't produce effective form out of non-effective forms. Yeah, that's not true. And most interestingly, at least to me, is that it gives the classical Euler-Lagrange equations. And what does it mean? So consider that alpha is an n form, and it's an effective one, and we just recall that n is dimension of m. Now let's see how we can get to variational problems and functionals. So assume that phi, our function, is compactly supported, and then since alpha is some n form, the nabla alpha of phi, delta, I'm always confused, delta alpha phi, right? Well, this right-hand side is well defined, right? This is an n form on M, and we can integrate it to get this functional. And the interesting fact about Euler operator is that the variational problem arising from F, phi will solve the variational problem arising from F if and only if it will solve the equation given by image of alpha under E, under the Euler operator. And now let's see what happens if we pick some nice alpha. If we pick alpha as L beta, where, as I said before, L is a smooth function and beta is dq1 of h dqn, so it is a classical variational problem in the sense that it's a first order variational. It will correspond to a first order Lagrangian if we pull down this form on M. And if we view it as a functional, we have this guy. So this is like first order Lagrangian, right? And if we rewrite this equivalence in coordinates, then we get exactly the standard form of Euler-Lagrange equation. We have just one equation because one field. Euler-Lagrange equation in the coordinate form. Yeah, so E satisfies this. And we can use this to, we will see this the next time, we can use this fact in the following way. So assume we have a partial differential equation, some nice partial differential equation we are interested in, and we find an n form which represents this equation. In other words, n form on J1m, such that if we pull it back down and consider the corresponding equation, nabla omega phi equals 0, it will be precisely the PDE we started with. Then we can compute the effective part of this form.
Delta.
Delta, yeah, delta. Thank you. We can compute this. Effective part of this form. So get a unique representant of the PDE, And then we can ask whether there is some alpha such that epsilon alpha will give us this effective part of, let's say, omega, which represented the PDE. So in other words, we are asking whether we can solve the variational problem up on the level of differential forms, differential n forms on first jet space, J1M. And yeah.
Radek, maybe at this point, maybe it would be good to, how do you get L beta from delta alpha phi?
How do I get L beta from, sorry, from what?
From delta alpha phi. Oh, okay, so alpha is L beta.
Yes.
So what's, and delta was again, that was...
This is just delta, is just, so this guy, yeah? Delta alpha phi. It's just the pullback of alpha along J1 phi, where J1 phi is section of the bundle J1M to M. Let me jump. This is our operator. Yeah, this is delta omega phi, right?
Okay, I was confused with the delta. We expected some Laplacian operator.
But in fact, you know, if I pick omega appropriately, then I will get a Laplacian.
Sure.
Yeah. You see, so this is some sort of a generalization. Okay. But I know it's, this notation is not, I mean, it might be confusing. I understand completely. But it's not my notation. I'm not the first one to use it. And it seems that some interesting things already have been computed using this notation. Although I assume that it might be done without the notation.
So, so remind me, the J1 phi, what does that mean again?
J1 phi is simply...
So it takes
is the first prolongation of phi. Phi is a function, and J1 phi is the first prolongation.
Okay.
But I can understand it as a section. You know, J1M is a bundle over M, right? And J1 phi can be understood as a section from M, as a section of this bundle, J1M down to M, right? So maybe I'll in the next part I will maybe try to give also some diagrams of where is J1M, where is M, and what we are pulling from where to where. So to make it a bit more. Yes?
Yeah, I think for this audience, instead of diagrams, it would be easier to understand using coordinates and maybe one example.
Yeah, but I'm using coordinates. I used already. Check it out. In the very beginning.
No, I meant like in a specific example.
Oh, yes. But that's the point, yeah? That's the point. I wanted to split the talk into two parts, right?
Yeah. I'm giving you like advice for the next part.
Yeah. I hope the next time it will be much more clear, because this thing is not too much complicated, but there is a lot of notation. I agree.
Okay.
Right. Okay. So let's get back, because we are almost at the end. So we wanna utilize this fact that we have some nice operator. This operator is acting on forms up on the J1M. So maybe let me say once more the rationale of this approach here. So you have a partial differential equation which is defined for coordinates on M. You can represent this equation up on the, I mean, like you can consider like first prolongation of the equation to the J1M, and then you can ask for differential form which represents this equation, this prolonged version. And then you can find unique representative of this equation. And then you have an operator which from every given n form produces such an n form that this is satisfied. Yeah, these two equations are satisfied. Meaning I can take form up on J1M and define functional down on M. And I can ask whether there is some other form up on J1M such that I get the Euler-Lagrange equations of this functional, right? And what we want to do is to reverse the process the other way around. We can start with equation represented by form and ask for for another form which would give us some Lagrangian for the original PDE. Okay, I hope it is not too confusing and that I did not say something wrong. Okay,
So basically you are trying to find the inverse of the Euler operator.
Exactly. Yeah. But not inverse of the Euler operator, but I mean, I want to solve or at least say something about the inverse variational problem, whether it is solvable or not, at least. So by this, we can see necessary conditions on given PD, or we can, using this procedure that I described here, we can state necessary conditions on differential forms representing given partial differential equation, necessary conditions such that there exist Lagrangian. We might not be able to compute it directly, but at least we can know for those equations which are not variational that they are not variational, right? So that's it, more or less. And the connection, so the effective forms are not only useful to represent uniquely the given PDE, but we can cook up from effective forms multisymplectic forms and get with our PDE to the multisymplectic setup and multisymplectic geometry. And just to recall or define multisymplectic form, it is completely, as I said in the very beginning, complete generalization, I mean, direct generalization of a symplectic form. So symplectic form is a two form which is closed and non-degenerate. And the multisymplectic form is a n+1 form, which is closed and non-degenerate. Okay, so this is the condition on closeness of the n+1 form, and this is the condition on non-degeneracy. And of course, this must hold for every psi for every like every vector field. If it satisfies this guy, right? Then
what is alpha in this definition?
Alpha. Oh, sorry, my notational fault. So it shouldn't be there. Alpha shouldn't be there. Yeah, just forget alpha here. Shouldn't be there. Okay, nothing else. So multisymplectic one form, if n equals 1, multisymplectic one form is a symplectic form. Okay. And this remark that certain effective forms give rise to, sorry?
When do you use this? When you have more fields, or?
Please, can you speak a bit more loudly because I can't understand?
When you use these multisymplectic forms, when you have more fields, or?
No. In fact, no. We have still one field, but we can, for example, if we will see this the next time, that the first and second Plebanski equations from self-dual anti-self-dual gravity, they are not variational in the sense that there will be a first-order Lagrangian giving rise to these equations, right? But still, the effective form satisfies the condition of the theorem I'm advertising here, which connects effective and multisymplectic forms. In other words, this Plebanski 1 and 2 has such differential form representation that it gives rise to multisymplectic form. And once we have a multisymplectic form for the equation, we can find a Lagrangian for the equation, although it will not be a first-order Lagrangian on the first jet bundle. Okay, so I mean, this is nothing very surprising, I guess, for people who are working with some inverse variational problem or with Lagrangians, that we might not have Lagrangian on some level, but on some higher order level or some a bit different setup, the Lagrangian still may be there, right? So this is, in a sense, this is the case. Moreover, we can say something about the solution space of the equation once we have the multisymplectic form. Yeah, so this kind of rationale is behind the value of having the multisymplectic form.
Information would I gather out of this about the solution space, or?
What kind of information?
Yeah, why would I want to do this? What do I gain out of reformulating stuff?
Well, So I think that, for example, it might be interesting in partitioning the space of solution into some classes where the classes contain solutions which are transferable to each other by some multisymplectic transformation or something like that, for example. So then once you know element in this class, you can generate the whole set of solutions in this class by applying multisymplectic transformations. But frankly speaking, I'm not that far in this context. I only know that it might be useful. I can recommend papers which are dealing with this. Yeah, but that's it. Another sorry.
Sorry, this symplectic form, right? If
symplectic,
right? And then I can ask you. I don't want to, you know, break up.
No, I mean that's the end of the talk. Yeah. So now it's at least from my point of view, that's it. Yeah. That's the end. So time for question, I guess.
So, yeah, the question is this: this symplectic form you're working with, it's not like the symplectic form in Hamiltonian dynamics, right? It's something different.
So what is a symplectic form in Hamiltonian dynamics?
Like in your setup, you have one field phi, right, and then you're mapping the jet bundle. So the natural symplectic form for me would be d phi t. Like that would be the, you know, symplectic form on a phase space, right? Whereas this is something weird. This is like a
but in this setup, are you? I mean, so why it is more natural? You know, why it is more natural?
I mean, that's what I use in Hamiltonian dynamics, right? I
where you have
I take my first time derivatives, right? I choose what the time is, and I construct d
that's
phi
exactly
phi t.
Exactly.
Whereas somehow combining the base coordinates with the derivatives in the fiber, right?
Yes.
The target. So,
yes.
It's not really a symplectic form in a sense of Hamiltonian dynamics. What is it like? I mean, that's a bad question.
Well, I mean, yes, that's your point is totally correct. So firstly, we know that we do not have to. We haven't preferred any of the base coordinates above any others. Yeah.
Right.
And sorry.
Right. Yeah.
Right. Yeah. We didn't. Yeah. And I think this is one of the main points in getting from this setup to the multisymplectic one, which is, if I understood correctly, the multisymplectic setup and the covariant phase space formulations with multisymplectic geometry is exactly like that, yeah? Like the Dunderweil formalism, right?
For that, I would have something else, right? The multisymplectic form there would be like d phi which d phi t which d phi x. Like I would just multiply all the different momenta for phi. I would never include base coordinate dx's in there, right?
Yeah. I mean, yeah, it's hard, you know, it's hard to it's definitely something a bit different, right? And it's hard to somehow compare it in what is better or what is worse, right? I mean, in this, you see that this guy, this omega, is something which is, you know, in a sense, canonically living on the space you are dealing with. It's not like you are not doing too much choices, right? You have J1M, and on this guy you have a canonical identification of J1M with R times T star M or T star M times R, and you can consider this form, which is, you know, it's constructed from this projection and tautological one form, and out of this guy you get everything. You see, and again you are using to obtain the symplectic form, you are using the exterior derivative, a natural operator, right, on J1M. And although you have to restrict you have to restrict down to the Cartan distribution to be able to employ this symplectic calculus, because otherwise the non-degeneracy might be violated. In fact, I don't want to say something wrong now. So I would end with the fact that it's, in a sense, geometrically, it is a natural approach to go this way, right? Although some physical interpretation and comparison with Hamiltonian guys, not so direct, at least not in my mind. Maybe there is some nice possibility to transverse from one to the other, or at least, to compare it, but I'm not very much aware of that. Sorry for not a complete answer in this regard.
Also, if I had more fields, would there be a natural object in that situation?
Good question. Good question. I will try to speak about it the next time. And there is, I don't know whether there is something interesting going on or not. In fact, we will see together. Maybe for some it will be obvious that it's not interesting, or maybe for some it will be obvious that it's maybe something interesting. Because what can you do? It seems that the construction, like which we have seen here, is in a sense functorial, right? And what I mean by that, we can follow this procedure of having something like contact form, something like symplectic form, and we can do this for like multiple functions, right? For finitely many functions, we can do a similar procedure, but some things are violated. For example, this non-degeneracy condition is not easily tractable, because the overall space we will be dealing with will have like these individual symplectic forms would be symplectic forms only on some low dimensional subspaces, but the whole space would be like constructed of these low dimensional or less dimensional subspaces, which in this case is not a problem, because we have like this whole thing on which omega is symplectic, and then you have like one dimensional complement done. But if you add at least one function, then you have like a dimensional space and two 4-dimensional subspaces or something like that. And these two symplectic forms, computationally, it works very nicely, but the non-degeneracy condition might be violated. Yeah, if you don't take care about it, which I'm not completely sure how to somehow deal with so far. It's not obvious, but you can construct like Euler operator for each function. So in fact, this property of Euler operator, I mean, check this defining equation of Euler operator 12. What I want to say, we can have multiple Euler operators in a sense for each field we want to consider, and then we really get in local coordinates classical Euler-Lagrange equations. Yeah, we get this. Yeah, for each field. Yeah, but there are these problems with non-degeneracy, and it's not obvious whether it can be used somehow nicely or not. So,
right. Okay. So I guess Andras' point was basically that there's many symplectic structures, and you have one symplectic structure. Some of them lives in the target space. Some of them lives in the what should we call it, the base manifold or space time, and here the symplectic structure you have is maybe somewhat a mixture, because one could argue that the p coordinates are derivatives in the phi direction, so it's some kind of mixture of the two.
There's no real relation here to Hamiltonian mechanics whatsoever, right?
Yeah, right.
Maybe why I got confused. I'm sorry. Yeah.
Right, but it could. I mean, I'm sure it's useful for what Radek want to say next. I have another question. If I may change the topic,
sure.
Can you maybe give some intuition for why there should be this unique Hodge-Lepage decomposition? This
So
Luchagin.
Yeah, Hodge-Lepage-Lichagin decomposition. So, frankly speaking, I don't think I can pull out
Okay, never
the
mind.
idea of the proof.
Yeah.
It's inductive, definitely. So you start with alpha, and you find out that there is a unique alpha 0 and some rest. And then what can you do is repeat the process and get this
Right.
alpha 0, alpha 1. But those, these guys are not that much interesting. I know that the representation of SL2C is involved in this.
I see.
And
That's interesting.
yeah. That's why I was talking about the top operator. Yeah, because we have seen the bottom operator, where it is here, which is contraction with this dual to the symplectic form. Oh, here I should have there should be big omega. Sorry. Yeah, this.
Yes.
And this is so the dual operation is like top operator, which is wedging with the symplectic form omega. And the commutation relation, if we compute like the bracket of top and bottom, they satisfy the SL2C relations. And that's
also
where
with the identity, right? You need
right.
operators.
Right. Sure.
Question, do they satisfy? What did they say?
Sorry?
What did they say they satisfy? What relation?
Sorry? SL2, right? SL2R.
I see.
I don't know what was the question of Ondra.
So I guess there's 3 operators you're talking about. If it's SL2R, then I'm sure there must be 3 objects you're talking about that satisfy.
Sure, but bottom, top, and identity, right?
Okay.
Oh, yeah.
I see.
Show us those 3 operators. I'm sorry.
So what I can do, yeah, because I don't want to say too much nonsense. I can check the details of this, and we can see the next time, yeah. Because I don't want to say some stupid thing, yeah. But
no, I think it's right. The top, bottom, and identity are like SL2 triple, so their commutation relations give you the same as SL2 algebra.
By identity, you mean just nothing, like identity, like okay.
Where's the top operator?
It's wedging with the big omega.
Okay.
Omega and so wedging with omega raises the degree by 2 and bottom guy lowers it by 2. I see. But shouldn't it then be more like relations of Heisenberg algebra rather than SL2? Because identity, right? Like they will anti-commute to identity, you're saying. So identity is not like H, right? H is like counting the, I don't know. It's not like identity in SL2R. So it's maybe more like a Heisenberg algebra.
oh,
Did you leave?
I'm back.
Oh.
No. Connection,
Okay.
but now I'm on a hotspot now, so.
Yeah, Andre was questioning the
operators. Yeah, I'm not completely sure. I think it's bottom, top, and I mean like it's wedging with the symplectic form, contraction with the dual to the symplectic form, and the identity operator.
What is the Lechegin red book called? I forgot. So maybe you can.
Yeah, it seems more like a Heisenberg algebra, really, because if you're doing the same thing for, like if you're wedging with forms and contracting in the vectors, right? That's like the action of Clifford, right? On modular function on form, right? So should be more like that rather than SL2R. What is this?
No, I'm not completely sure. I don't think that it's in this book, frankly speaking.
I think it is in. At least I remember reading it there.
Really? Yeah, it's possible. It's possible. But I think.
Yeah, we don't have to spend too much time on this, right? You can
Just
look it up.
if you give me a second, I can check.
Maybe you can share a screen and show us in the book if you want that.
I would have to download it first.
No, that he can open it and share the screen with us, right? So we'll see screen with the book open.
Are you speaking to me or?
Yes.
Yeah, sure. I think I have an answer to the question in this paper. So in the book that Standa. So first, let me share. So Standa is speaking about this book, but I don't think it's in this book. Let us see the
contents.
The contents, right?
And yeah, chapter 5.
Yeah. Oh yeah, right. You are right. You are correct. Good.
So
good
125 or 132.
Here we are.
Those cats around there.
Sorry?
Those cats, there's pictures of cats scattered around.
Yeah, it's famous for the pictures of cats. Yeah, you have the identity there, but yeah.
So we have this is the key thing, right?
Yeah, it says it too.
Right on the, and so we would have it on the algebra of exterior forms, and it's oh yeah, it's not completely identity, right? You see, it's like multiplication because this guy, if we compute the commutation relation of the bottom and top, they are not completely dual, right? You can have some factor in front of them, so it's not completely identity. That's true.
Okay, so it is like a degree operator, just shifted. Okay.
Degree, I don't know, but what do you mean by degree operator?
Like it's just like K form goes to K times that form, but it's just shifted by a certain.
Yeah.
But my problem was that if it was just identity, right, then it wouldn't, those forms wouldn't fit in like SL2 representations, right? I need to see the degree, which will be like a Cartan generator reading it off.
And this is like the main ending statement.
Then you find like a primary, like that's what the decomposition is about.
Sorry?
You find like the highest weight, like you pick your form and you start acting on it, right? And you find the highest weight guy, and that's the effective form, and the rest is like descendants in the Verma module or something.
Yes, I think so. But again, yeah, it's really, so this is important. But I don't, it's like as I said in the beginning, right? I didn't prepare the proof of the Hochlepa-Schlichagin theorem, and I just knew that SL2C is involved and that this bottom and top operator. But yes, I cannot give you the full proof, so I don't want to say something stupid. Yeah, but you see that the idea goes this way. Okay.
But by the way, you can see how this Laplace decomposition works, because if you write like in jet space, say form the U, then you can add P the Q and minus P the Q, and one part is this Cartan part, and the second is the Q part, which is on the bottom, something like this. At least in one-dimensional case, it works very nice. And as Radek said, the proof is inductive. Like if you have larger dimension, then you have to add something and subtract something, and this adding part compose into Cartan form, and the remaining part is the bottom part of the form. So something like this.
And of course, it should terminate because of the finite dimensions.
Yeah, exactly.
Okay, so maybe some other question, because I think I exhausted completely my knowledge in this regard.
Yeah, I have a comment, not really a question.
Sure.
Maybe a question. So at the end, you were talking about this inverse variational problems and with some equations in gravity or self-dual gravity. And you said that you can do this procedure, but you will get a Lagrangian that is of higher order, not or out at higher order. In jets.
Not what I know. So to say it a bit better, yeah. If you have a multisymplectic form, you can cook up some, and again, that's something I'm rather vague about, yeah. But you can cook up some Hamiltonian out of that, with some like multi-Hamiltonian, and similarly as you have like Hamiltonian fields, you have multi-Hamiltonian fields and stuff like that, and you can, as in Hamiltonian mechanics, you can go from Hamiltonian to Lagrangian. In a sort of a similar way, you can go from this multi-Hamiltonian to some multi-Lagrangian or something like that, right?
So it wouldn't just be normal Lagrangian or
no,
jet too.
It wouldn't be completely
okay.
It definitely wouldn't be something on J1, but what is interesting, and that also requires some further attention, is that Olga Rossi together with Saunders studied the inverse variational problem using the Lagrangians on higher jets. And as a matter of fact, they also have a multisymplectic form, and this multisymplectic form is, I mean, at least from the coordinate expression that they used, is very similar to the multisymplectic form that we will see in the next part. I don't know what is the complete relation, because the space that they are living on is different, right? But the multisymplectic form looks very similar, so that's interesting, definitely.
Yes, as far as I know, the method they use, you always get a Lagrangian of higher order. But
you just have to go high enough, right?
You can just add a trivial Lagrangian and lower it, right? Because Lagrangians are in such a way that they don't reproduce equations of motion uniquely. You can add some trivial Lagrangians and you can reduce your order via that. It doesn't work all the time, but in the simplest equations like Schrödinger equation, Young-Mills, Maxwell equations, when you do a procedure from you start with the equation, you want to get a Lagrangian, you always get a Lagrangian one higher order if you use their methods, but you can reduce it just by looking at how it looks and adding some like trivial Lagrangian. And
Lagrangian, you mean Lagrange multiplier? That's what you...
No, I just mean you add a Lagrangian that is like a
term
boundary
derivative.
Yeah, exactly, and you would reduce the order. So is this something that would happen with your multi-Hamiltonian to multi-Lagrangian setup, or is it different?
I don't think so. I mean, at least as far as I know, the Lagrangian that I get is in a sense formal, right? I just assume that some inverses can be done, and in a similar way as one assumes in the classical Hamiltonian mechanics, right? And then I can cook up from the multi-Hamiltonian some Lagrangian analog, right?
So even without going to multi-Hamiltonian, multi-symplectic business or anything, how do you get the Hamiltonian in this setup? Like when you have just like what you just described, having just one field and you have this form and stuff, right? Is there a way to look up Hamiltonian out of that, or?
Yeah, sure. I wonder whether
you need more data, like distinguish direction in the base.
So again, I suggest to move this to the next part, because again, I don't want to be imprecise at all. All right. I'm not sure whether I can directly click on some paper. No, I cannot give you out of hard satisfactory answer to that. Yeah, so maybe next time.
So maybe one more question, maybe.
Sure. I mean, as far as what I know, I can I can tell, but
So how far you are from solving this inverse problem?
it's not about solving the problem itself. Yeah, the method is not that powerful, at least as far as I could compute. But it's quite useful in deciding when something is not variational.
I see.
Yeah. So maybe it'll be possible to use this method to show that self-dual fields does not have this variational nature. Yeah, for example.
Seems interesting.
Maybe or under some other additional assumptions on the self-dual fields. But the self-duality itself seems to be. I mean, the equations that come from self-dual or anti-self-dual theories seems to have precisely the terms in the coordinate expressions, the terms in the differential forms, which cause the problem with the variational, with the existence of Lagrangian for them. Simply because how the Euler operator looks on the jet space. Yeah, you can compute the general form of the Euler operator on a completely general form, and it has some specific coefficients. And the self-dual, for at least, I haven't proved the general case. I don't know. Yeah, but that's the prospect.
Maybe I can have also more comments on this. You have a lot of subtleties when dealing with these inverse variational problems, because if you use one method and you decide that this equation doesn't have Lagrangian, maybe for example, if you have like a system of, let's say, two equations, so the method that we used, or I don't know if it's also true in your method, you can just compute everything and you say, okay, it's not variational, it just doesn't have any Lagrangian, it doesn't work. And then you switch the order of the two equations and suddenly it works. Or you multiply one with two, or you can do very like basic manipulations to the equations, for example, like multiplication, or if you have like a system of equations and you would multiply it by some constant matrix, then you could generate a variational equation, for example. So yeah, just that in using the method of Musella and Rossi.
That's a good point. It's really hard to exclude the existence of Lagrangian formulation.
What does it mean physically? That's super weird. Like I believe that.
I think in this inverse problem of variation, there is formulation of the equation as they stand. So you don't manipulations.
Yeah, but that is not really interesting from a physical point of view, because you don't know what equation you have to start from.
Yeah, you can also
always multiply it with some matrix or function.
Physically, the equation of motion are not the end of the story. Right? It's just some critical law of Lagrangian. Lagrangians are really what it's about, right? It's no surprise that there's no arguments in a way.
Yeah, but there are some physical equations that don't have Lagrangians. Yeah.
Sure, yeah, but they are usually not something fundamental, right?
Yeah, I remember.
Sorry.
I remember Linus was asking me about some equations in I'm not sure what it was. I think it was type 2 supergravity, which are not
Yeah, famous type, right?
yeah.
But then I think there's a way around it with some like. So type PD, right? It has some dual type form, right? And that one, if to stand on its own, then doesn't have convergence. But you can divide it in. So you know, if you believe in string field theory, right? Then it needs to originate from that formulation. There's way more. Some of them impose that as Lagrange multipliers. So it's always that. At least in physics, it seems like those fundamental equations, they always come from Lagrange kind of accumulation. And maybe there's more extra impose it. Somehow they don't come.
Yeah, you have to speak a little bit louder, sorry, because you are cutting out in the end.
Yeah, I don't know, but maybe your microphone is a bit damaged or something, because it's hard to catch sometimes what you say. Ondra. Yeah. So also quite interesting question is, I mean, like, what is the relationship between these? You know, if you know that there is not Lagrangian on J1M, but you know that it's on some higher jet, what does it tell you about some physical nature of the equation itself? Yeah, or something like that. For example, similarly, you can take the Plebanski second equation and you can decompose it into evolutionary system. Yeah, you just add one field and you decompose the equation, and then you have quite nice Lagrangian in this setup. Just a simple trick, and the Lagrangian pops out. Yeah, but the Euler-Lagrange equation would require one higher term, which is one more. I mean, like, the Euler-Lagrange equations wouldn't end with they would need another additional term, another derivative, higher derivative, to produce the system of equations which are the composition of the Plebanski original. Yeah. So that's also something interesting. But again, yeah, this splitting into the system is not somehow canonical, right? You choose a coordinate, yeah, you do some quite standard procedure, but it's not canonical at all, right? So that's but the Lagrangian is nice.
So it's a higher order Lagrangian?
Yes, one more. That's in fact why the method that I described in the end, or method, the idea that I described in the end of the talk today, that you can do like multiple Euler operators and include multiple fields. It's short for this type of problem, because you see the original motivation for me was I knew that the Plebanski second equation doesn't have the variational nature in the sense of existence of first order Lagrangian on J1M. Okay, but if you split it into the evolutionary system, there is Lagrangian, but you need two fields, and the Euler Lagrange equations are one order higher. But these Euler operators that I can produce are not higher order. I mean, I'm just fixed to this order that I had, right? So I cannot produce, I mean, and iterating the Euler operators doesn't produce higher order Euler equations or something like that. It doesn't work this way. So hard to say how to somehow connect these various things.
So you're saying the equations of motion are of the same order as the Lagrangian, then? Is that like there's second derivatives in the EOM second derivative?
Yes.
So isn't it that
exactly.
Okay, but then isn't it just because you just like other field just works as the auxiliary field and just, you know, like multiplies the equation of motion in the Lagrangian? Like isn't that a
possible? Yeah, it's possible. I don't know. But it's quite possible, right? But I don't know. I can give a link to the paper, maybe, where this is described, and maybe because I mean, I don't know that much things about all the possible approaches in the inverse variational problem. Yeah. So maybe people who are dealing with this kind of things might see it much more quickly and in a much more natural way. And if you give me just a second, maybe I can post to the link I can post to the chat the link on the paper I have in my mind. It's by Sheftel and Nutku, which are dealing with this kind of self-dual equations, also in higher dimensions. It's something like multi-Hamiltonian structure of, I think I got it maybe. Yes, I have it. So let me share the screen for just a second, and then I can post the link. So for those who are interested, right? Check this out. I can take, so what we start with is this equation, number one. This is the second Lebensky equation. And do you see it properly, or is it too small?
It's fine.
It's okay, yeah? So this equation we will see also in the next part. And we will see that this equation doesn't have first order Lagrangian. No function on J1M such that we would get what we need. But if we split the equation in this way, as I said, into first order system in T, then 5 is the Lagrangian that we are dealing with, which will correspond to this system. You see? So that's quite interesting, right?
And that's second order, you're saying, because there's an
from 5 to get to 2, yeah, via a system of 2 Euler-Lagrange equations, you need second order. It just doesn't end up in 2 if you allow just for first order.
And it doesn't seem you can add some total derivative to it that would make it first order.
Well, you can clearly differentiate the second last term. You can shift the x to the other guy, but you cannot do that with the first term. I mean, yeah, no. You would always have a second order derivative.
Mm-hmm. So it is like truly on J2.
So if you're interested, I can share or maybe here is the name, right? Multi-Hamiltonian structure of Lebensky.
Can you hear me now? Was this better with the?
Yeah, that's better.
Yeah.
I'll do it next time.
So that's the paper I showed you now, if you are interested. And then there is a multi-Hamiltonian structure related to the evolutionary system that they get, and all the analysis can be done, yeah, quite nicely. They compute many things. Yeah. Okay, so I guess that's it from me. Are there any other questions or comments, suggestions?
Maybe I don't know exactly, but the suggestion is that because you show everything locally, so maybe the coordinates are not the problem, because by Darboux theorem, every symplectic form has always the form you show, that every contact form is as you show locally. So the coordinates are not issue, I think. But I'm not sure.
But Darboux, that's also a local statement, no? It's talking about a patch. So it's not clear where you can like glue things together. in consistent manner. Right? If you can show that there's Darboux coordinates globally, then your manifold is of T star M type.
It has trivial topology.
Yeah.
Okay, so it seems that.
Yeah. So yeah, thank you again, Radek. It was very nice. Maybe you can stop the recording.